Okay. So, new strategy.
So you started at 1.
We started inviting 1. Then I went to invite. Well, first 1 crosses out 4 and 6. But then I skipped 2.
You invite 3.
Invite 3, which takes out
6.
6 and 9. No, 8.
And you go to.
And then I skip 4, go to 5. That would take out 2. Already have 8. And then 10.
So then 7.
7 would take out 10, which has already been taken out, and 12. And 9 takes out 12 and 14. 11 takes 14, 16, 13. 13, 16, 18.
15.
15 would take out 18 and 20. And 17 and 19.
So, let's see.
So this is 10 people.
1, 2, 3, 4, 5, 6, 7. Yeah, but now we've beaten the optimal strategy.
We've beaten our optimal strategy.
Which means this must be an optimal strategy. This must be.
Well,
This is our new optimal. Our optimalist so far.
yeah. So, what can we say now about the optimal strategy?
It's this. We don't want to do the greedy algorithm here, and with the optimal.
Okay. What else can we say about the optimal strategy?
It's you take all the odd numbers in the optimal strategy.
But you could also take all the even numbers.
Okay, interesting. Very good
Even
observation.
numbers get more. 1, 2, 3, 4, 5,
There's
6,
still 10.
So, do we know this is the optimal strategy?
No,
No.
but it's our best.
It's our best so far. So what can we say that put that into math language? This is the best so far. So what can we say about the optimal strategy? How many is it going to have?
It says it would have 10 or more.
Okay, so it has to have at least 10.
At
Yeah.
least a half of the people.
Well, we don't know how it might work for other things, but this is a new optimal strategy.
Yeah.
This is before all we could say is the optimal strategy had at least 9,
Yeah.
and now we've learned something.
That has at least 10.
It has at least 10.
Yeah.
And why? Hello, Math Cat. What was better about this when you were doing it? Did you notice anything different that was happening when you were crossing things out here? What was different about this compared to the greedy algorithm?
Well, this is it's alternating
Yeah.
in out.
But when you were actually going through it, something different was happening than what happened in the greedy algorithm.
So when we got it crossed out here. Let's just say 9 crossed out 12 and 14. Then 11 crossed out 14, 16.
Okay.
So you crossed out everything twice.
Yeah, probably except for 2 and
And
maybe
20.
20. But you were piling up the crosses. So you weren't spreading out the crosses, you were kind of piling them up.
Yeah.
And that was happening a little bit with the greedy algorithm too.
Yeah, you got some overlap. Not as much.
I can see how you can get 2 and 20 twice.
Huh?
So you can do 5. 5 is 3 away from 2. 7 is 5 away from 2.
Oh,
So
nice.
2 did get crossed out twice.
Nice.
And 17 is 3 away, and 15 is 5 away. So
Interesting.
So it looks like
all the people we didn't
everything
invite.
got crossed out twice.
Well, how many times did 4 get crossed out then?
Well, you've 1 time, 2 times.
But then you also have 3 times.
Ah,
So
wow.
we're getting crossed out a lot.
Yeah, we really piled up the crossouts here. So this is really cool.
I wonder if there's a pattern in the crossouts.
Maybe. Yeah. So now we're rolling downhill, aren't we?
Yeah.
Okay. Well, I am going to stop here because we've been talking for a long time. But what do you think? What do you think one of the lessons was in this for this problem? What do you think? Why do you think Jim Prop wrote about this problem?
Don't be greedy.
Maybe that's what he was trying to say. What else?
Well, if just because you haven't just because you've got something that seems like it's the best, you have to try more things.
Yeah. Yeah. It's hard to know things are the best until you've tried everything.
Yeah.
It's hard to know.
Yeah.
So, but it's a good example of mathematical thinking, of just trying and noticing that you've done a lot of things that are the same and now trying something different. So, hey, great work, guys. Very nice job.